is a picture that was taken during an eclipse, just to kind of remind us that, you put your hands up to the air, and you normally have like a circle, but you've got these little moon shapes, because every moment that we're in, we're being affected by our environment. And this photograph can only be taken in that moment and not the moment afterwards. Life is super complex. Living systems are complex, and they're so well evolved that we really largely take them for granted, right? They're highly automated. You don't actually try. You don't will your hair to grow. You don't will trees to grow. All of the things that we depend on are systems that are happening without our intention. And the more that we find out about these systems, the more complex we realize they are. And that's effectively what I've been spending the last 20 years really researching living systems, designing for living systems, and by that I mean really systems that are living as well as systems for living. I'm not an ecologist. I started out as an industrial designer, but I've been asking the question of how do we support life with the way we design things and by the technologies we use, and ultimately by the technologies we start to develop. So in the summer of 1999, I moved down to Austin, Texas, and I lived in this silver trailer, and I was there to build flexible building systems for a project for the U.S. Department of or Environmental Protection Agency. And it was compelling to me at the time because it meant exploring this kind of central absurdity in how we make things, which is to take incredibly valuable materials, like everything in our kind of manufactured and built environment, unbelievably precious in a sense, because we're really stripping it out of the surface of the earth, and we entomb them into buildings or into products that are inevitably going to change. And so, these buildings could change over time to fit new needs. So the pieces could be swapped out or repaired. And at the very core of a flexible building system is the notion that anything we design or construct is subject to change, is destined to change, and it's really just a temporary arrangement of atoms. And that kind of describes how I think about design in general, is how do we design for these flows of things that are very temporally based? They only are with us for a short period of time. It may seem like a long time for ourselves in our short lives, but everything is constantly shifting. So everything that we make is changing, and thinking about a building as a point in time and designing it to be changeable or mutable or disassemblable seemed to me at the time to be worth living in a shack in the woods, getting paid $40 a week, and working in 114-degree heat. And I lived there. I went back, actually. I went and lived there for a year, like an insane person. And we were doing a lot of this sort of trial and error to build, not this building, this is actually just a shack in the woods, but the buildings that we were working on were prototypes, right? And we were building like high-performance buildings, so buildings that use a very little amount of energy, generate energy on site, are able to get all the water they need locally, those kinds of things. You make the building and you test it, and it's labor-intensive and it's iterative, but over these long kind of time horizons. And in the background, we were constantly running these calculations on ecological footprints, right? We'd look at the site and we'd sit there and go, okay, how many trees do you have on a piece of land, and how much oxygen and CO2 is cycling through that little spot to support how many humans, and how much square footage of roof area do you need to capture all the water during the rainy season to carry the family through the dry season. These kinds of calculations all the time, and again, slow, kind of handmade work, even the math. And so I got caught up in all of this sort of calculus because I'd put myself on a mission, which was to apply my creative energy towards optimizing the health of living systems at different scales. And so, even though I was ostensibly an industrial designer, in this case I was working with green builders and ecological land planners, and I never really fully went back to industrial design because in a lot of ways I was very much focused on the systems that we were designing for. But the situation that we were in was pretty marginal, right? Now we're looking almost 20 years back. And so this is from the inside of my trailer. And we were kind of up against the edge of society because we're trying to engage its deepest problems. And when we looked at what we wanted to have happen, and even now, what we want to have happen, to really apply common sense approaches to how we create and design the built environment, we were experiencing a lot of headwinds, right? That there was a need for extreme specialist knowledge. There was the time to make these kind of handmade physical prototypes. We had to understand, there was very little understanding of alternative materials, of alternative energy systems. We needed to effectively reform the entire design education system. There needed to be better media talking about it. We should be running better competitions. We should be researching new materials, and maybe we should be developing new technologies to enable this to happen. So these were all the headwinds at the time. And addressing each of these kind of across the board is effectively what I spent the next 20 years on. It's what a lot of people have spent time on, is how do we take these kinds of processes and these kinds of explorations that are worthy but so slow and so much not the kind of standard practice in how we design and build, and how do we very, very quickly start to deploy them and make that more effective? So, and as I was going through, I kept kind of asking myself, like, as I was working on these different projects, like, is this the leverage point? Is this the leverage point? Like, what's the thing that's going to allow us to really shift the way that we make stuff? I did spend some years just doing more kind of standard, like, atomized projects. I spent some time as a woodworker, doing really like high-end fancy things for very wealthy people, and doing various kinds of materials explorations and geometric explorations, and different kinds of visual stuff, and ran a whole project at one point looking at how we could make degradable replacements for plastic food packaging. And so I spent a bunch of time, with like these cornstarch mixes and seaweed pastes, and I was talking to food scientists and medical engineers about non-toxic biopolymers, basically trying to say, okay, plastic waste and in the food system, how do we hack that and create things that can just dissolve at the end of their life? And I realized very much this is a problem that I couldn't very easily solve alone. These are kind of systems problems. And here I am completely solitary in my kitchen, like shooting on film, trying to do different kinds of materials explorations to figure out what kinds of polymers we could create out of food grade materials and have that degrade. And stuff that I actually ended up exploring again, that I'll talk about in a few minutes. But a lot of these things are kind of systems questions. They're not just this one material. They're kind of like, where does the material come from and where does it go? So I did a bunch of work looking at like cycles of materials. How do we generate greener materials and have those things be used and then have them be recaptured? What's now being referred to as kind of circular economy principles. And I also was very much involved with a group of folks who were really looking at all the different beautiful kinds of solutions and responses that were being created and thinking, okay, we have a pretty strong point of view that many of the things that we need, the ways that we can respond to ecological challenges, humans have figured most of this stuff out, right? That the biggest problem that we have is the distribution of these ideas. And so we worked on this massive compendium, 600 pages long, that's all kind of a breakdown of solutions. This is now over 10 years old. And I think in a lot of ways, it did have a certain kind of effect. It was very heartening to see that. We go back to these kinds of concepts. But again, I don't think that the collating of these kinds of ideas is necessarily enough to see the transformation that we're looking for. So I almost 10 years ago, I ended up going and starting work after finishing this project. And I went to work with Autodesk here in San Francisco. And the reason, in a lot of ways, was that coming from something like design or industrial design, realizing that so many of the questions that we ask when we're dealing with material reality are not just aesthetic ones, right? They really have to do with the flows of energy and the flows of materials. And those are actually engineering questions as well as design questions. They work beautifully together when they do. And so I was very excited to go and work somewhere where we could actually start exploring those energy flows and materials flows, and I spent a lot of the last 10 years doing that. One of the challenges that I encountered was that when we started creating tools for doing green building, for example, we kind of came back to that same problem I talked about earlier, where actually people didn't really know how to do it. They didn't even understand the basic physics of energy or how buildings worked. And so we needed to, in fact, create learning materials to teach people how to do that. And so I spent some time doing that, just really trying to break down the systems of how energy is used in our industrial society, or looking at the different kinds of materials and energy footprints around the things that we make. Because, in this case, if you can keep a mobile phone in use for many, many more times longer, if you're able to swap out its components, if you're able to repair it, you're able to avoid massive amounts of physical waste. All this stuff is on a site called the Sustainability Workshop. And these are kind of almost like, you could not engineer this kind of efficiency. It's not actually possible, but you can be designing things in harmony with those kinds of things. So we spent a lot of time teaching about those kinds of concepts. And a couple years ago, I got very involved at looking at additive manufacturing, which I know many of you here are familiar with, and we've got beautiful examples of stuff out in the gallery. And one of the challenges here, I was looking at additive manufacturing kind of as a whole. So you're looking at computer-controlled processes that are used to create a three-dimensional object layer by layer. Much of this stuff is not all polymer-based, but much of it is. And I'm not a chemist. I've never worked in chemistry, but one of the critical problems in looking at additive manufacturing, there's all these opportunities that happen, but one of the critical problems is around the materials that get used. The opportunity side, we know, like, all of a sudden you're able to make anything you want. You've got the capacity to make something kind of on demand, one at a time, not have to deal with the huge amounts of inventory. There's lots of really beautiful potential in the technology. But the chemistry is still standard practice. And one of the things that I did was start looking at that and working with people in a field called green chemistry, which is, interestingly, a small rarefied field of chemistry in which people actually look at toxicology as the first question they ask, which is interesting if you realize that all the rest of the chemists in the world aren't asking that question. What are the hazard considerations, the human health considerations of the chemistries that we're formulating, right? And so, and the other thing that I actually learned from talking with them was that the majority of the chemistry that is actually being done is, in fact, not just polymer chemistry, but it's petrochemical. So, like, the majority of all chemistry done by chemists in the world is basically looking at petrochemicals, because the carbon bonds and the nature of that chemistry is so easily manipulated. It's actually really wonderful to work with. But, so you're looking at this really elegant new form of technology, new way of making things, but you're dealing with old chemistry. And so that was kind of the most difficult problem that we started to look at. So I was working with Autodesk, and they had a 3D printer they were developing called Ember, which was able to make these incredibly beautiful, really, really elegant, gorgeous forms, very, very detailed, that in some ways really duplicate the shapes of things that you see in nature. But at the cellular level, at the chemical level, they're radically different. They don't function at all like what you would see in a biological system. They are really very, very, very different, structurally very different. But visually, you get the sense of it. And so this is where we started to really dive in to understand where could we bring these worlds together. What are the things that we can actually learn from the way that biological systems really create shapes? This is actually looking at feathers. And fortunately, we were working with a system that was all open source. So all of all of the code, all of the CAD files, and actually all of the resin chemistry were open source, which meant that we could then take that and go and work with researchers, in this case we're working with UC Berkeley, to really start figuring out different opportunities. And so we teamed up with them and with a group called the Biomimicry Institute to start researching different kinds of ways of creating materials. This is ongoing, this is really an ongoing question. We just started pushing at it because these technologies are still so new and so nascent, and if we anticipate that they will scale and that we'll see more of them, this is really the time to be looking at these kind of fundamental questions. Because when I say that the materials aren't good, they're really not good. Like, you don't want them in your body. You don't want them in your kids' bodies. You can look this stuff up. It's fairly standard set of photopolymer chemistry, and it's known to be an ecotoxin. So we did a lot of work to kind of publish that and also talk about methodologies for being able to understand different ways of making stuff. And one of you can see, one needs to be wearing gloves and headgear and stuff to be able to handle it. One of the things that we were exploring, that one of the students that we were working with at UC Berkeley was exploring, was just really unpacking how is it that, in this case, how do muscles attach themselves to rocks when they're being hit by huge amounts of wave force? And it turns out it's because they're able to affect a shift in the pH of water to create an adhesive. And so those kinds of explorations, if they could be applied to the way that we manufacture stuff, even if it's a completely different form of additive manufacturing, it's a really, really interesting kind of exploration. So I'm hoping to see more of that in the world. The work that that the team did got published in the Yale Journal of Industrial Ecology, so that's coming up soon. Relatedly, I think, relatedly in the sense of that we're looking at materials at different scales. I mean, I went from looking very, very small at the chemistry of stuff. On the other end of the scale of the things that we make are looking at things like steel. So steel is one of I think it's like the second most pervasive material that humans use after concrete. And you can imagine it uses a huge amount of material from the Earth's crust, and therefore uses a ton of energy to process, and therefore is related to a significant amount of emissions, right? So it affects climate, just like everything we do does. We look at something like the way that most buildings are built. You've got standardized pieces, standardized shapes, like I-beams used in buildings that often mean that you end up with way more use of those materials than are needed. So there's a guy called Julian Allwood in the UK who did a breakdown and realized that at least in the UK, there was at least 40% more structural steel being used in buildings than needed to be to meet the code. Okay, so huge amount more material being used. And the reason was that it actually was more expensive to engineer it out than it was to just use the materials, right? So buying more steel was cheaper than buying the brain power or computing power of removing it. And this kind of question of how do we get the thing that we need so it actually will stand up, the building will stand up, it'll be structurally sound and safe and beautiful, and also be able to use the least amount of materials is a really valid question. How do we do that, and how do we do that in a way that people feel comfortable about? Because when we're doing things in a one-at-a-time way, we tend to over-engineer, we tend to be very conservative. So it was really interesting to see when I was, in the last few years, people doing explorations around generative design, whereby you would look at one shape and run it through an engine to be able to run algorithms to see what are the many, many different kinds of shapes that could be created that would serve the same purpose. And you end up with many, many, many different variations that are generated by an engine, effectively. So what it means here is that technology is suddenly enables us to deal with higher levels of complexity. You're able to do so many more tests on things because you're not doing it one at a time and having that be taking years. So those kinds of simulations that are happening many, many times over in parallel may help us start to develop technology in support of living systems, right? And what's also interesting about it is that when you see these kinds of things being developed kind of through these kinds of technologies, this is something that that Autodesk developed called Dreamcatcher that my colleagues were working on, that they start to, in fact, look like forms from nature because they're running through an evolutionary process. You know, part of why I showed you the very slow process of making stuff at the beginning is just to say, you know, for me to go through, or for the teams of people who are building things to go through an evolutionary process, it would take us generations. And we don't have that kind of time right now. You know, so how can we work in collaboration with these kinds of systems to create things that give us lots of variation, that reduce the amount of materials that we're using? You know, in what ways can we be accelerating evolution effectively to promote efficiency, to work with complexity? And you know, it's just cool to see how you see the shapes. You're seeing how the computational systems are coming up to the same conclusions as millions of years of evolution, right? And so there's kind of a dance with the systems where the systems themselves become alive, and we are working with them and steering them. And the same kind of technology is starting to be applied to things that are a little bit more ephemeral, like energy. So what you're looking at is different kinds of simulations on spaces, where you can do a lot of different kinds of simulation, looking at energy and thermal, daylighting, these kinds of effects that take place in rooms, and so, or in buildings rather. And so what this means is that you can start to actually simulate and see how materials and energy are being used in very sophisticated ways, and really start getting towards a state where the things that we create, the buildings that we live in, are effectively net zero, and that doesn't take, as it once did, many months of work. So it used to be, for example, in the case of buildings, that it would take a specialist, sort of somebody from the priesthood of building energy analysis analysts, to do they do an energy analysis of a building, like you have like a big hospital getting made, and it would take them sometimes weeks, sometimes 2 or 3 months to run the calculation. And by the time they were done, it didn't matter because the design team had moved on, and so it was never used. And so those kinds of calculations, if you can be designing something, and as you're designing it, you're getting feedback, you're getting told, and you're getting a steer around how to shift the nature of what you're making to use the least amount of energy, it transforms almost everything we do. And so it's lovely to see that we're at a point where, at one point in time, fossil energy was very cheap, right? It was very inexpensive to just burn stuff, and we could do anything. You know, it meant that we built whatever building we wanted, and we just throw air conditioners into it, or throw heat exchangers in, or chillers. And now we're at a very different state, because in fact, computing allows us to account for more complexity. And so, what I'm interested in is what this actually means going forward. All the different other kinds of flows in living systems that we can be thinking about and designing for. Because if there's anything that I want to convey, it's really that everything that we make has some kinds of effects and impacts. Those things are often not seen, but if we can be bringing in the information about those flows, it radically transforms the way that we deal with the built environment. So it's not just about the artifact; it's about the artifact as it exists in space, in time, and also like its effect, its history, and its future. So I really believe that that a lot of these kinds of complex systems aren't really very easily manipulated by just us as individual designers. I think that in a lot of ways they need these other minds to be in collaboration with us right now, especially since the urgency is so extreme. And I really think that if we can start to apply computing technology in the service of life, that we really have the capacity to start addressing these problems much more rapidly. You know, we have, I think, everything we need all around us, but we need to teach our machines, our collaborators, to understand how life works. And that's something that's much deeper than what I've been able to show here. It's just you see some references to it. Because really, extraction has received almost all of our creative energy as a species, right? We've gotten very, very good at different forms of extraction. And I think it would be amazing if we could start to apply the same level of intelligence towards the restoration and the regeneration of our living systems. And that really is the most ethical use of technology we could see. Thank you very much.